Okay, which best describes a triangle with side lengths of 6 inches, 8 inches, and 9 inches? Well, first thing we have to remember is no two side lengths of a triangle, can be shorter, or sorry, no two side lengths can be shorter than another. So, for example, if I had one that was, let's say that's about 4 inches long, and then I had a side length that was 1 inch and 1 inch, that is impossible. That does not work. That is what we call a non-existent triangle. I know that sounds weird, but basically if I ask you, hey, what kind of triangle is one with a base of 4 inches and then two other sides of 1 inch and 1 inch, well, that triangle does not exist because these can never meet up no matter how much you move them down this way. So no two sides together, any two sides, can be less than less than one of the other sides. Another way we can define them is ambiguously defined, and that's what the answer to this is. Because ambiguously defined means that there are it's a little bit unclear as to exactly what kind of triangle we're talking about. An example of this might be a triangle that is similar to another one that has 60, 60, and 60 for its angles. Well, can there be more than one like that? Yeah, absolutely. We can just have a bigger one that's like that with the same angles. 60, 60, and 60. Another example, we might have one that's 85, 20, and let's see, it's 105, 75. Can I have more than one triangle like that? Yeah, absolutely I can. I can just have a bigger version of it. Okay, I can have, even though the side lengths are longer, I can have one like that, and that's what we call ambiguously defined. It's not 100% sure. If I tell you, hey, I got a triangle here with angles of 75, 85, and 20, well, there can be more than one. There can be an infinite number if you want to think about it. I can have one that's with the side lengths of about 1 inch, and I can have one with 3 miles. It doesn't matter. That's what ambiguously defined means. Non-existent means it can't exist, kind of like this one right here. And then I'm not even really worried about you with the angles here. So a lot of these are going to be out of 3. Another one is unique. And unique is what we have here. Anytime I give you the exact measurements here, there can only be one triangle like that. Because the only way those would match up would be the angles would be exactly the same and those measurements. There's only one triangle on the planet that would be like that. Okay? So that's the answer to this one. Unique. And again, the reason why is I can have triangles with the same measure but be different. In other words, they'd be similar but not congruent. The only triangle on Earth with this has the exact same corresponding angles. In other words, the corresponding angles are the same and the corresponding side lengths are the same. In other words, it's a unique triangle. We'll talk more about that in class too. Which best describes a triangle with angles measuring 60, 40, and 100? Well, if we add those up, first of all, the first thing we need to do is add up the angles. If we are given angles, they have to equal 180 for a triangle. If you add 60, 40, and 100, that equals 200. There's no triangle on Earth because all triangles, regardless of how big or small they are, have to have all their angles add up to be 180. So this one is non-existent. Which best describes a triangle with side lengths of 3 inches, 4 inches, and 8 inches? If you add up 3 and 4, that equals 7. And if you add up 2 and they are less than one other side, so you basically have to add up all combinations to find this out. But this is impossible. You would have a triangle that looks a lot like this. This is 8 inches. This is 3. And this is 4. These aren't long enough to meet up. In fact, they'd have to be larger than 8. Much less be less than 8. So that will not work. That is called a non-existent triangle. Which best describes a triangle? And by the way, I'm not even worried about you being able to identify whether or not they're right triangles or obtuse triangles or whatever. We're just looking for ambiguously defined, which means there's more than one. We're looking for non-existent, which means that one cannot exist, like this right here. And then we're looking for a unique one where all the measures are the same. All the measures of the same, the side lengths are the same. Not the angles, but the measures of the side lengths. So again, which best describes a triangle with a side length of 5, 12, and 13? Well, if I add up 5 and 12 and 5, that equals more than 13, so that works. If I add up 13 and 12, that ends up being more than 5, so that works. So it looks like we've got a triangle that can exist. It looks like we don't have anything that can add up to less than one of the other sides. So it looks like we're going to end up with a unique triangle. Okay. Lincoln constructs a triangle with one side of 5 inches long and another side of 7 inches long, which is not a possible length for the third side. Which is not a possible length for the third side. Okay. Well, what we have to do is add, let's say 5 plus 3 equals 8. 5 plus 6 equals 11. 5 plus 11 equals 16. 5 plus 12 equals 17. Now all those added together are greater than 7. Okay, so it looks like that one would work. All right, well, let's try 7. Okay. Let's take a look at that a second. Now we've got one dealing with angles. We've got angle measures of 65 and 38. What must be true of the measure of the third angle in her construction? Well, we know that they have to equal 180. So let's go ahead and add 65 and 38. Get 3, carry my 1. That's going to be 10. 103. So now we know that the last angle has to be plus x equals 180. We would simply subtract 103 from both sides. Or basically, once we get the measure of the two angles that we know, just subtract that from 180. So 180 minus 77, minus 103, forgive me, is 77. It must measure 77 exactly. It must measure 87. It can have any measure less than 103. That's certainly not true. It can have any measure greater than 27. That's not true. It must be 77. Josh constructs a triangle with angles measuring 54, 23, and 103. He wants to construct a different triangle with those angle measures. What will he find if he does? Remember, we can have any given different number of triangles with these angle measures. They can be big ones or small ones. Remember, the side lengths are what's important. The side lengths are what's important to make it what we call a unique triangle. So let's read the choices here. It is not possible to construct a different triangle with those measures. No, that is not true. Any other triangle he constructs with those angle measures will be congruent to his original triangle. No, if he makes a smaller, well, let's say he makes a triangle with those measures and he makes a another larger one, they will be similar, but they won't be congruent. Congruent means they're exactly the same, so that's wrong. Any other triangle he constructs with those angle measures will be similar to his original triangle. Choice C. Remember, angle measures, you can have the same angle measures all day. It's the same side lengths that where we come into trouble with making another triangle the same. Cynthia wants to construct a triangle with angles measuring 34, 21, and 125. Which best describes a triangle with these measures? Let's make sure that those add up to 180. Let's see, 34, 21, and 125. We got 0, carry my 1. This is 4, 5, 6, 7, 8. Looks like we're in good shape. So, again, we're going to get rid of these. I'm not concerned about that. We're dealing with, we want to know if it's unique, non-existent, or ambiguous. We know that it's not non-existent. We know that that triangle can exist, so that's not a good choice. Our angles are the same. We can have another one with the angles the same. So it's not unique. We can have a big one like this or a small one like this. So our answer is ambiguously defined. And again, you're going to have a lot of notes on this. You're just going to have to read those from time to time. Carson wants to construct a triangle with side lengths of 4 inches, 7 inches, and 12 inches. I can already see right away that this is non-existent, because if I add this to this is 11, and you cannot have two side lengths be 11 and another one be 12. That would look, again, like the triangle we drew earlier. That is a non-existent triangle. If you add these two up, or add any two up, and they don't equal, or they're not greater than the other side, then you have a non-existent triangle. A rectangular prism is, now we're talking about cross sections. A rectangular prism, which means, let's say that this is 2, and this is 3, and this is 7 feet right here. And it's sliced with what we call a plane. It's just kind of like, if you think of it as like a sheet of paper. It's a plane, but a plane is not, it never ends. It goes on for infinity, but you don't need to worry about that. You just need to know that something is slicing this guy right in half. And what we want to know is, let's say we've got a cylinder, and this is a bad example of a cylinder, but if I cut that in half, I did a cross section, and you turned it over and you looked at it, what are you looking at there? You're looking at a circle. Okay? Again, if you've got a cylinder, and this is a very short cylinder, but if you ran a cross section right in the middle of it, and then you were to take that and look at it straight on like that, you're dealing with a circle. Well, this concept is, there's several different concepts you can think about here. One is with a rectangular prism, which all that means is it's a rectangle kind of stretched out. It's like a box. But it's not a cube. It's not a perfect box where all sides are the same. So it's sliced by a plane that is perpendicular, which means it's straight up and down, to its base. Okay? What is the shape of the cross section formed? Well, if I took that, broke it in half, and looked at it, what am I going to be looking at? Am I going to be looking at a trapezoid, which is, that's an example of a trapezoid right there. A square, a perfect square. A rectangle, not square. Okay, that looks reasonable. And a parallelogram, but not a rectangle. So maybe something like this. This is a parallelogram where you have two different lines that are parallel to each other. They may not be a rectangle, but a rectangle is a parallelogram, but this is an example of a parallelogram that's not a rectangle. You're going to be looking at a rectangle, because if you broke that in half and stared straight into it, you'd be looking at a rectangle. Again, a rectangular, and this is, I believe we're moving on to worksheet number, or Coach Book 22 now. That worksheet. Number 1, rectangular prism, and you can see the measurements here, 9 millimeters and 5 millimeters, is being sliced by a plane parallel. In other words, before we had one perpendicular to the base that went kind of like straight down like this. But this one, this plane is running parallel to the base. In other words, this is perfectly parallel to this base right here. What will be the shape of the cross section formed? A parallelogram that is not a rectangle but not a square of course, it's not a triangle. The reason why it's not a square is because if you would take this and look at it, you would have one side that's 9 and you would have one side that's 5. By definition, a square is the same on all sides, so that's not it. a rectangle but not a square, and a parallelogram that's not a rectangle. Again, an example of a parallelogram that's not a rectangle is like this. Since this is parallel exactly with the base, and this is a rectangular prism, more often than not, when you slice or cross-section a rectangular prism, you're going to end up with a rectangle that is not a square. And again, that's one of those things you really have to visualize. It's one of the things I really can't teach to you, to be honest with you. You have to kind of think about, well, what if I had this box and I cut it in half and I stared straight into the part that I cut? What would it look like? What is the shape of the cross-section formed when the square pyramid, we got a square pyramid, and this, I know this looks kind of funny, but this plane just kind of drops right through this. And it does not pass through the top. Okay, if it passed right through the middle, you might come up with something like a triangle. But this one kind of slices it down here toward the right side of it, if you will. Well, we're obviously not going to get a parallelogram. We can kind of see the shape that it makes here. Okay, it's going to look somewhat like this. And again, this is not a triangle. If it were if we came down through here and stared at it, it might be a triangle. It's not going to be a square, definitely. It's not going to be a parallelogram. It's going to be a trapezoid. And that is what a trapezoid looks like. You have all different types of trapezoids. You've got ones that look like this. I mean, you know, but basically that's what we're going to be dealing with there. Again, we've got one that is sliced through here. It's very important to note that this is parallel to the base. In other words, this is completely level with this. So this is not going to be slanted in any way to make it look funny. You're going to end up with a rectangle. I guess you could end up with a square too, but of these choices, this is the best one. Matt molded a cube from clay. Then he took a piano wire and sliced through as shown by the dotted line below. What is the shape of the cross-section formed when he does this? Now, to be honest with you, this question is a little flawed because we don't know exactly how far back he is here. If we're looking at this, if we're judging by the image, I'm going to take that out and it's going to look somewhat like this right here, because I'm not all the way back, I'm just kind of really close right here. So if it was back far enough and I made this a little bit wider, it could be a square. But it looks more like it's going to be a rectangle. Certainly not going to be a triangle, and not going to be a trapezoid. Okay? If we were a little bit back, maybe we're right here and we did this cross section, drop that piano wire through here, might be a square, but we're looking more like a rectangle. Which is the shape of the cross section formed when the pyramid is cut by the plane shown? We have to be very careful because this is a different type of pyramid here. It's only got a base of 3 points. So therefore we're going to come up with a triangle here. If it were a pyramid with 4 points, it would be a square or a rectangle. But in this case, we're going to be dealing with a triangle. So we've got to pay very close attention to the dotted lines. This gives us an idea of the shape of the three-dimensional figure. The prism below is sliced by a plane to its base. We're just going to assume, let's just say that this is 3 inches here, and this is 2 inches. What's the shape of the cross section? It's going to be a rectangle. Now, if this were 3 inches, 3 by 3, and we did a cross section here, or a plane parallel to the base, it would be a square. So we have to understand the difference. When you have to pay very close attention to the measures, okay? If these measures are different here and we run that, it's going to be a rectangle, because you're going to end up dealing with a cross section that looks like this. It's going to be 3 and this is going to be 2. The diagram shows a cube with each edge 2 feet long. The cube is being cut by a plane perpendicular to its base, so it's going to be straight up and down. And forgive my drawing here, but this is 2 feet by 2 feet. Base and a height 2 feet. Identify and draw the shape of the cross-section formed when the cube is cut by the plane shown. Label its dimensions. So it's going to be a square, and it's going to be 2 feet tall by 2 feet wide. If we took that guy, cracked it open, and stared at it. Suppose the plane is parallel to the base. So in other words, suppose a plane went through like so. What would the shape of the cross-section be now? Explain your answer. Again, it would, because we're doing a cross-section parallel and it's a cube, that means that this is 2, this is 2, this is 2, this is 2, this is 2. That means all the sides are 2. We would still be dealing with a square, and it would be 2 by 2. Bear with me 1 second.